Please, Bill, you take from here.
Okay, great. Thank you. Okay, I'm going to talk about CMake, and these are CMake. Modern CMake is an open source set of tools to build, test, and package software. There's something called CMake, which is the build tool, CTest for testing, and CPack for packaging, and then a web application called CDash. So, quick, you had the introduction. One of the founders of Kitware, originator of the CMake build tool. I like to run around the mountains barefoot or in sandals. All right, moving on, I'm going to try to get through these introductory slides pretty quick so people can have time for questions, and I can cover a lot of the topics on CMake. First, a quick introduction to Kitware for those that aren't familiar with it, or maybe all of it. Kitware, we do collaborative R&D software. We create algorithms and applications. We help people develop software processes and infrastructure. We have this sort of wheel chart here. We have a high-performance computing and visualization group. They're the ones that worked on ParaView, which is probably common in your community. The medical computing group, which their main open source platform is ITK and Slicer. We have a computer vision group. They do a lot of work with DARPA and tracking in videos. We also have a data and analytics groups that create web applications for data and analytics. And then we have a software process group, which is the group that works with CMake and CDash and CTest and the stuff I'll be talking about today. We work with all kinds of customers and collaborators, academic institutions, government labs, and lots of companies. We support open source platforms. Our business model is to build these platforms and then provide support or do collaborative research based on these platforms to and always with an eye to make the platforms better and work on them into the future. So there's VTK and ParaView, ITK and Slicer, CMake, which I'll be talking a lot about, Resonant for informatics and InfoViz. Quiver is a toolkit from our computer vision group for image and video analysis. We also have some other areas in simulation, ultrasound physiology, information security, material science. So what is CMake? CMake is a cross-platform open source build system that lets you use the native development tools you love the most, or maybe the next build tool that comes out that's really cool. So it's a build system generator. It doesn't actually do the build. It generates to different types of builds, so it can work with Ninja, Visual Studio, Xcode, Makefiles. The input is plain text input files where you describe your project, and then it produces project files or Makefiles for use of a wide variety of native development tools. So I always kind of thought of it as being able to take advantage of the most precious resource of the project, which is the developer. And if Kitware is any indication of what developers like, they all like different tools. And they use different tools, and they're most productive using the tools they like. So if you take someone that likes an IDE, force them to use the command line, they may not be as productive, and they'll complain about the build tool. But CMake allows a wide variety of developers and them to use the tools they like and to be more productive in that way. And along with that, I mean, not just building, but we had to build CMake so that it was able to test your software and also package it. Modern CMake. So this is just a quick introduction to that. I'll get into a little bit deeper, but since the title of the talk was Modern CMake, I thought I'd dive right in. Some key points. CMake is code. It should be treated like that. The CMake lists, they should have comments, and they should follow good programming standards, just like you would for the rest of your code base. Another key point is that CMake targets are objects with public and private properties. Targets being libraries or executables, mostly libraries. Next point is that third-party libraries should be imported as targets. Repeating that object pattern. The library should know what flags it needs to be if you want to consume that library. And that you should export your libraries so that others can use them in CMake projects. A little history of CMake, to give a shout out to where it got created from. So the Visible Human Project was created by the National Library of Medicine, and in 94, 95 they created a data set that they made public. It was a CT, MR, and then they actually took the bodies and froze them and sliced them and took pictures at each slice. So they created this really interesting data set where you had ground truth data on CT and MR scans. But then they came with the revolutionary idea, I think, that really to make science move forward, you had to take the code that worked with that type of data and actually implement it and make it open source. To avoid the, what I like to say, you know, you have a PhD professor and he's got a student and he hands the student a paper and says, you know, go off and implement this, see how well it works on this data set, and then the student comes back and says, well, it didn't work. You know, and then maybe they spent a month on it. And did the student implement it wrong? Was the paper wrong? There's all kinds of variables there. But if you actually have the code, then you can run it and find that out. And then, so the idea is there are code. So Kitware was part of the team. There were 3 commercial entities and 3 academic institutions that were tasked with creating ITK. Kitware was one of the lead engineering teams, and we were basically tasked with making it build on Windows, Unix, and Apple. We weren't exactly tasked with creating a build tool, but at the end of the day, that's what we did with CMake. And in 2001, CMake was created. It had its first release branch. Since then, CMake has gotten broad usage in the C++ world. I suppose our big tipping point was in 2006 when KDE adopted it as their build tool. And this was good for them and great for us as well, in that it forced CMake to adopt a lot of standard patterns that you see in that were in auto tools, and that to make shared library versioning work and install rules work fast. So basically it was a great opportunity for a large toolkit to adopt CMake that was outside of the Kitware's projects. And since then you can, if you went on Indeed.com today and searched for jobs that had CMake in the requirement, I think there's like 263 of them right now, and a lot of big projects use it. We get about 7K downloads per day from our website, but it's also packaged with other systems. Microsoft adopted it. I mean, this is really crazy. I figured anytime they were going to, at some point they were going to come try to sue us for reverse engineering their Visual Studio files, or at least have us committed to a mental institution for reverse engineering them. But instead, they've adopted it, and CMake actually ships with the latest version of Visual Studio, and they're working with us to further that integration. CMake features that I think this group will be particularly interested in, that CMake does automatic dependency generation. You know, if you write your own make files, that's often hard to do, in that, you know, include files are automatically done with C and C++, CUDA, and also Fortran. So CMake has a built-in Fortran parser and makes sure that everything's up to date and that things are built in the right order. So if you build a target in some directory, everything in that target depends on will be up to date. If a header file changes, the correct files will be built. And you really don't have to do much work to make that happen. So Fortran module order, this is a difficult thing for build systems to get right. This was from Intel Fortran User's Guide. You need to make sure the module files are created before they are referenced by another program or subprogram. Okay, well, how do you do that? I've heard some of the old way was people just type make until it actually works, which obviously is sort of a pain in the neck. with CMake, you can write CMake and then make, or CMake and Ninja, or CMake and CMake -- build, and then CMake will make sure that the Fortran files in that directory are ordered in the correct order so that the modules are all built and created before they're referenced in another Fortran file. The Ninja build tool. This is, I think, one of the great examples of how CMake's community works and how we can move forward. So Ninja was a tool created by the folks at Google to build Chrome faster. And as soon as it got released as open source, I think within a week or so, there was a version that worked with CMake. Someone had started putting a merge request on CMake. And I think within a couple months, we had it pretty well working on Windows, Linux, and Mac, and all the platforms. So that was a great example. So then any project that was using CMake automatically now is able to use this much faster parallel build tool called Ninja. We also improved the parallelism for Ninja as of CMake 3.9 by what used to happen is with each target, it would build all the .o files in parallel, but then it would stop on the link, and it wouldn't do any other object files until that link was actually done. In newer CMake, it's able to build all the .o files because they don't really depend, unless there's hard dependencies on those libraries specified, and then link when it needs to. You can also use pools to limit concurrent links if that's causing a problem for your system, if it has too much memory being used. Another random thing that CMake does really well, it's got really good install commands that work cross-platform, packaging tools, the ability to find and link system libraries, handles shared library versions across platforms, keeps up to date with your favorite compilers and some really strange ones. It promotes cross-platform development, integration of static and dynamic analysis tools, coverage tools. We have great policy system for backwards compatibility. So CMake tries really hard to not break your code, but nudge you forward by giving you some warnings if we've found better ways to do things. It's an open and dynamic community, accepting changes large and small, and it supports many workflows and IDEs. The basic workflows, you edit your files in your source tree, you run CMake or one of the CMake GUIs, and this creates a build tree, and then you open the projects and use the build tree. And really, you only need to run CMake once to create this build tree, because CMake will put hooks for itself in that build tree. And if any of the input to CMake changes, it'll make sure that that gets updated. One of the things that CMake does really well is out-of-source builds. I remember early on, I mean, way back in the 90s when I was doing makefiles and AutoComp, it kind of did this, but you had to go through a lot of hoops to make it work. This is sort of the norm for CMake, and it's really neat because you can have your source tree, one source tree, and then you can run CMake several times, creating different build trees where you can try different things, maybe different build generators, maybe different optimization levels, maybe different compilers, and these can all use that same source tree, but have completely different build trees. So modern CMake. Here's sort of a list of what CMake can look like and used to look like. So this is the earliest CMake list file I could find. It was from 2001, and you can see it's changed a lot. Basically, it was sort of declarative and looked a lot like a make file way back then. In 2008, you did something along the lines of this, but you were using variables for sources, and now you have this more object-oriented CMake where you create a library, and then you're telling it what sources, and then I can say, if I'm on Windows, I want to add this extra source file, instead of having to use variables that, if you misspelled them or something, it wouldn't necessarily know what to do. But in this case, the target name has to exist, or you'll actually get a hard error. The best way to think about modern CMake is that targets are your objects. So you have a library, and the constructor would be an add library call, and then you can set the compile definitions, compile features. These would be sort of like the member functions on your object, and the same thing for an executable. And then the actual properties themselves would be the member variables. But the idea is that you encapsulate this in the target. So the developer only needs to focus on the single target and not the whole system. You know, what include directories will the user need when they compile against my code? What -d flags will the user need when they compile against my code? What compile flags does the user need when they compile against my code? What version of C++ is the user going to be required to use with this library? What flags and options will users not need? But maybe I need to build. And these can be controlled with public and private declarations. But if you take anything away from this talk, this slide's pretty important. The fact that you want to take that single target and program to that, and then use it elsewhere, and then all this stuff just sort of propagates. And you're using basically the target. The classic style, you would have said something like include directories, and then targets in this directory and subdirectories get that include flag. But then if you move something out of a directory over to somewhere else, then this breaks. So what people end up doing is just keep pushing those include directories up to the top of their project, and then they've got just huge command lines that are ridiculous, and use way more flags than they need to build the code. Whereas with modern CMake, you're only going to get what you need or what the developer thinks you need. And that developer only needs to think of a small object at a time, which is that one library. Before usage requirements, the commands you would say, include directories, compile definitions, compile options, and they would inherit down. The consumers needed to know, does the dependency generate build tree files? Does the dependency use any new external package? So there was lots of things that you had to know. In modern CMake, the goal is to have each target fully describe how to properly use it. No difference between internal and external targets. So the layout is independent. You can have it anyway. Really what you want is this graph right here where the executable uses library B and library A, and then library B uses library A, that's fine. And then all the flags and compile options, link options just work. And it doesn't matter what your actual directory layout looks like. So mostly modern CMake's about not using these commands. Add, compile, anything that affects like a whole directory and down, and then treating the targets like objects. The usage requirements, target link libraries is the foundation of the usage requirements, and it's formed by public, private, and interface. Target include directories, this propagates include directories. So this one, I'm saying my interface to Leaf would link to the zlib directory. Anything that links to Leaf will automatically have the zlib-dir on the include line. Compile options, I can propagate compiler options. In this case, I'm saying private, so only the trunk object or files in there are going to be optimized for the current hardware. Anything that links to trunk will not get this flag. Compile definitions, so this one I'm saying public. So root will have root version defined, and anything that links to root will also have root version defined. Interface libraries are a target that doesn't create any build output, though it may have properties set upon it, and it may be installed, exported, and imported. So you could use it for something like turning on C++ 11, or you could use it for header file only libraries. Along the lines of this, importing and exporting of targets is something that's important in keeping with this targets as objects. So in this case, I'm going to create an imported target where I create an add library, static imported. I set the property, the target. I'm setting the imported location using the set property on the target math. And the add library there essentially constructed a library called math. And then down here I'm using that in trunk, I'm linking to math. So in this case, it looks like a regular CMake target. So it's really indistinguishable from something that was built in your system, which is not the way CMake used to be, but the way it is now. You can also do per configuration import rules, which is better than the optimized debug keywords in target link libraries. In this case, I'm going to find a debug library for math and a release library for math. I'm going to create one target called math, and then I'm going to set the import location to math release and the import location debug to math debug. And then I link trunk to math. But I'm not, right, at that point, the person using math doesn't even know if there's a debug or a release version. They just know that they want to link to math. But yet, when I compile this, if I'm building debug or release, it'll build the right version. So install rules, you can export targets out of CMake. Install rules can generate imported targets. So if I have a library and I do install these targets, the destination libtree, export libtree targets, and then I do install export tree targets, destination libtree. This installs library and target import rules. So the library is going to be in prefix libtree libparasite.a, and then in prefix libcmake tree, there's going to be tree-targets.cmake, and that's where it's going to do an add library, and add an imported library, and then someone finding that package can just load that into their CMake file and then use that library, Parasite, as if it was built as part of their system. Conditional includes. So you can specify include directories. If we're building a library or using the installed version, this is pretty important to note. So when you're building your software, your include directory is going to be somewhere in your source tree, obviously. But after you install it, you're going to want to put it in the install prefix include package. And you can see right there it's using what's called a generator expression, and that's the $angle bracket. And this allows CMake to expand those variables out when it's in its generate phase. If you remember to go back to the slide of what CMake process is, it configures. So you hit configure, it basically executes all the CMake code, and then you hit generate, and generate actually creates your Make files or your Visual Studio files or whatever your build tools are, your Ninja files, and it creates those. And during that creation process, that's when these generate things get expanded. Generating the export package. This is constructing components needed for CMake aware config package. CMake package config helper can help with the generation of your name config.cmake file. Exporting of find package calls has to be replicated inside the name config, but the CMake find dependency macro helps simplify that. So we've got tools there to help you export your libraries so that other people can use your libraries if you're building with CMake. So you'd include the CMake package config helper, and then call this function configure package config file to take a config.cmake.in and go right into some install directory, and then that would create something that looks like this. Exporting targets. So I can create a library. I can set the properties of the interface include directories. And I'm setting the compile definitions.
The export, yeah, that's what it looks like. Yeah.
Right.
Yeah.
Right. This is what the exported target looks like over here. So the tree targets.cmake. This gets generated for you. Okay, install rules. So CMake has a great cross-platform install ability. Specified rules to run at install time. So I'm just creating a library here, and then I want to install some targets, and I'm giving a runtime destination and a library and an archive destination. To install, you can install just files. You give a list of files and then a destination, and that's going to be relative to the install path. Using config modules, find package supports CMake config modules that are generated. We just went through that. And the find package can find those or use find modules. CMake Scripts. CMake -E command, this is just a cross-platform utility for copying files, removing files, just a couple of common things that, to keep your either custom commands or CMake code from having operating system specific calls in it. You really want to avoid that if you want it to work cross-platform. CMake -P script, these are cross-platform scripting utility. It doesn't generate any of the build stuff like the cache and ignores all the commands specific to generating the build environment, but you can still run small scripts. CMake also supports object libraries, and what this means is instead of building to a shared library or a static library, you just create the .o files or .obj files, and then when you link against them, you can see down here it links just the .o files. So I've got my, I'm linking leaf, and you can see that it links in root.cxx.o and trunk.cxx.o. Even though those were called libraries, but they're object libraries. This can be useful if you want to, for various applications, if you don't want to have to create system-level libraries around groups of related objects. Okay, moving on to testing. So automatic testing is obviously beneficial. I've got this slide. I've been showing it for a while. The idea of the slide is that if you have automated testing, your actual time spent testing is reduced quite a bit. Although what usually happens is people just don't test if they don't have automated testing, so the time spent is probably the same, but the code quality goes down. Here's an example of ParaView being tested with CTest -J8 on a Windows box, and each one of these is a separate test going up. ParaView is going through, I think it's using a library we've got like CTest that allows you to save scripts out, and then it'll actually grab the image and do image differences and make sure that it's getting the expected image. Testing with CMake is really easy. Basically, it needs to be enabled by calling include test or enable testing. And then you can just call add test with a name, and then the command that you want it to run. Executables should return 0 for a test that passes. You can also set up regular expressions if you don't want to depend on the return value. CTest is an executable. It's distributed with CMake. They can run the tests in a project. And then I'll talk about CDash a little bit later as well. So CTest, so if I just run CTest at the top of a binary directory, it will run all the tests in that project and give you a little report and show you how each one was run. The -J option allows you to run tests in parallel, and you can give it -JN to specify how many, like that example I showed of the multiple ParaViews running. The -R option is a regular expression that allows you to choose a test, so it's best to name your tests appropriately so that you can group them. You can also apply labels to them, and there's a -L label option. Running tests from make files or projects, you can type make test or build run test project in Windows. CTest -- help will give you more information. It also supports integration of Google Test with the ability to discover the tests. This is new in CMake 3.10. It essentially asks the test executable to list its tests and then finds some new tests without having to rerun CMake. CMake also supports some interesting static analysis tools. I think with the advent of Clang, we're starting to see a lot of really interesting things coming out because you actually have a library with the whole C++ language behind it, and people are creating interesting tools for doing checks. For example, there's include what you use, which will go through your code and make sure that each include file is actually necessary. And CMake's got a built-in way of running and include what you use. We also create something called link what you use, which only works on Linux, but is pretty handy if you think you've gotten out of hand with linking too many libraries into an executable. But of course, with modern CMake, each target would only use and export what it needs, and that wouldn't be a problem. There's Clang Tidy, CPP lint, and CPP check. There's some setup instructions available on this blog I did a while ago on the Kitware blog. So what's CDash? So the idea is this continuous integration environment. We've been doing dashboards here, before CI was even a word, which I think is one of the reasons BTK became such a popular toolkit. Is early on we discovered that if you didn't test stuff, it was usually broken, and there was also a big move in GE to do Six Sigma at the time, where they basically had everyone in the whole company had to take Six Sigma training. Six Sigma was a manufacturing process for getting your errors in the Six Sigma of the curve, and we all had to take this, and it's thinking maybe we could do something useful and get some of, even at GE Research where there was basically a lot of papers being written and throwaway code, maybe we could turn this into something useful, and created the idea of things you could measure on the dashboard. So what can you measure with compiling? Well, you can do style checking. You can count the number of errors for configures or warnings, build errors and warnings, tests, passing and release, tests failing and passing. CDash works with other CI tools. It can work with Jenkins, BuildBot, GitLab CI, or just CTest scripts and cron jobs, Circle CI, Travis. And I think CDash provides something that these other tools are somewhat lacking on, in the fact that, like Jenkins, if you have something fail or a test fail, then what ends up happening is you get a pointer to a build log, which might be pages and pages and pages of text, and somewhere in there is the error. Whereas CDash not only provides a way of parsing those errors and a clean interface to them, but allows you to search for relevant results. So in this case here, I'm looking for all the sites that contain Microsoft in the group nightly expected, and I'm looking for test failures greater than 0. So it's showing me all the sites from Microsoft that have test failures. And this also allows us, you can see it's showing a good example of something CDash is doing, So like I mentioned before, Microsoft is building CMake, distributing CMake as part of their tool set. So they're actually testing CMake nightly on their systems and providing that information to the CMake developers through CDash. I can compare results across systems. So I can look and see that for KWSys test console buffer, that it was only failing on these two systems, but on these other systems it was passing. I can also track test timing. So you can see this test normally took hardly any time, and then suddenly on September 13th, its execution time went up to 11 seconds. And that can be an indication of something going wrong, and CDash can send you an alert when this happens. So if your code suddenly gets slower, it's probably something you want to know about. CDash has Subproject support for larger and more complex projects. The Trilinos package uses this. And the idea is that we've got our main project, Trilinos, and you can see for that project there was one error and a bunch of warnings, and this is actually the full build here. But then we can break it down into subprojects. So if I'm a Tethos developer, I can look at it and say, nope, not my problem. None of the errors are in my part of the system. So it allows the developers to look at the part of the system that they care about and to get things fixed quicker. CDash queries, so in this one, I'm showing all the ones with the build name heavy for the past 2 weeks. So that's a pretty useful way of looking back in time and seeing what things have been doing over time. Oftentimes code will creep into a code base, maybe it'll get past your CI, the initial CI, and something will start failing. Then you can go back to these dashboards and figure out when things started going awry and when the test started failing, and then go back and figure out exactly which version of the code started causing the problem. You can do most expensive tests. It looks like, so this one's showing most expensive tests yesterday. So build time is after 2 days ago. Build time is before 1 day ago. And then I'm sorting based on time, and I can see that which of my tests is taking most of the time. And that's useful for getting your test cases down to something smaller. CTest also has command wrappers output. So if you can actually see the actual command line that was run and the standard error instead of just doing log scraping. Coverage display, we do gcov, various formats of that, a commercial tool called Bullseye. And the idea is you can see your coverage and be able to drill down to each file and see which lines of codes are covered and do various viewings of that. You can also support integrating Valgrind, Purify, memory checkers, the runtime checkers, and it will show initialized memory reads, potential memory leaks. And the idea here is that you really want to run these tests every night, right? A lot of folks I know that they'll run some sort of memory checker when Valgrind when their code's doing something funny or they suspect something's wrong. But usually that's too late. This you could run it every night on your code base, and it would catch the bad code much more quickly and also point to which checking caused the problem, which makes it easier to find. CDash supports the display of image differences. This is up to the project to actually compute the image difference, but CDash can support showing the image differences. The other tool that we have in the suite is called CPack, and CPack is also bundled with CMake, and it creates installers like WYSIWYG installers on Windows, drop and drag installer on the Mac. It can create just a plain tar.gz file. On Windows, we do Wix and Nullsoft. Mac can do OS X, drag and drop, or the package maker. It can also do Debian and RPM packages. So it's a way of basically using your install commands. So basically, CPack piggybacks off of your install commands. So to get it to work with CPack, you make sure your install works and your code works out of an install tree, and your executables work with relative paths and can work from any directory. And then you would set a few CPack options as needed, and then include CPack, and then you would be able to get these installers created for you. So, now that you're inspired, you can read how to write a CMake build system by going to the manual online, which we update all the time. You can explore the CMake documentation. And thanks for coming to the webinar, and I guess we can open it up for questions and discussion now.
Hi, Bill. Thank you. Ashley, are you going to open the microphone for everybody, or?
So I would say at this point, Bill, if you want to share the Google Doc, your compadres have been trying very hard to keep up with the questions. But maybe we can start looking at some of the questions, and feel free for others to throw your questions in chat. We do have about 100 people on the line, so it's probably not wise for me to open the mic. But
you can't raise your hand.
Yeah, raise your hand or throw it in this document. But I don't know if there's some questions on there that are still being worked on. And then
my question, other resources I thought I filled out, recipes.
So, Bill, we just got a question through chat, which is how is CMake compared to other build tools such as SCons and GNU AutoTools?
Well, CMake is a build generator, so and interestingly enough, SCons was sort of the, there was a bake-off there when I talked about KDE using CMake. That was the other contender. And they ended up going with CMake. I think I haven't used SCons directly, but the problem they had in there was that since SCons was basically Python, it had each project sort of wrote its own SCons, so it kind of made it difficult to share code, whereas sort of the CMake philosophy is the hard stuff's done in C++, and once it's done there, it's shareable by everybody. And I mean, I think so that's one of the differences there, and that CMake allows you to use native build tools, and we were able to take advantage of Ninja and or people that want to use Visual Studio or other types of IDEs can use it directly from CMake. And I think CMake also has this other rich set of testing tools, package import and output of the target files. So it has I think, in a better way of linking in external packages. A lot of that's been thought out in the install rules. As far as auto tools, I mean, I think that CMake does have a lot of features, I think, that I went over today that may be hard to do in auto tools, but obviously one of the big ones that auto tools, it basically depends on having a whole Unix environment, and if you ever want to go somewhere else that doesn't have one, Windows or some other system, it might not have that.
So, Bill, a few more questions have come in, and so you may see in here, but have you noticed CMake builds being significantly larger than the auto tools? In HDF5, the difference is enormous. Not sure if that's inherent to CMake or a problem with our build script.
Not sure what they mean by large.
Is file size, like binary size?
Sorry, if the person who asked that question wants to chime in, feel free to take yourself off mute.
Yeah, we see enormous ones. You guys hear that?
The binary size is large?
Yeah, when we build, like if we have an outer source built for the auto tools, it's significantly smaller. It's like an order of magnitude, which is a problem if you have a system that's like doing a lot of testing and you're building many things. The CDash, the CMake stuff is huge.
Is that make files or ninja files or?
The auto tool stuff is just make files.
Right, but when you're doing CMake, which one?
With the target of the auto tools, the build make files.
Right. Yeah, I mean, I think usually CMake runs faster, but it's yeah, I hadn't really noticed that one. So I don't. It may be that CMake produces a larger footprint, but it shouldn't be that much larger.
Unless they're cleaning up their object files.
Yeah, I'm not sure. I'd have to look at that.
Yeah.
So Bill, we've gotten a few questions as we've gone along about can you recommend any good resources, reference materials for CMake?
Yeah, which one?
Yeah.
I referenced that for Craig Scott's professional CMake book is excellent. And
we'll make sure we get that.
It's only in electronic form currently. I don't know if you have any intentions on doing a paper version, since he wants to keep it up to date with newer versions of CMake.
Thank you. And there's some other ones coming in down there, Bill. I don't know if you can see them.
Yep. Developing tools help with cross-compilation on HPC systems. Yeah, right? The cross-compiling for HPC systems.
Developing tools help with cross-compiling. Right, so that would be like our work with the SPAC team for better CMake integration.
But that's not cross-compilation.
No, right, well.
So Bill, at this point, we only have a couple of minutes left, and I know there's still lots of questions coming in. But for those folks on the phone, we will continue to answer any questions that come in throughout this webinar in this document, and we will be sending a copy of this video along with the completed question and answers to all the people who registered for this webinar. So keep your questions coming in, but I think at this point it would probably be we could throw up this completed slide, and that will give Bill and team time to kind of really address these questions more comprehensively and get those answers to you as, in the next few days.
So then,
Yep.
So let me just then show my last slide here. So as Ashley mentioned, so the presentation, the slides, and also the recording of this webinar is going to be available soon. We have that arrow, so if you'd like to give us some feedback about this webinar, please feel free to do so. And also, if you'd like to have further training on CMake, I think we can help with that. So please fill the survey, and in particular, the question number 6 in that survey. That's the field where you could give us some, if you'd like to have further training on CMake. I also take the opportunity to announce the next webinar that's going to be about a month from today. And it's going to be open source best practices from continuous integration to statical inters by Daniel Smith and Ben Pritchard from the Molecular Institute of Software, funded by NSF. And that's the link, exascaleproject.org/events/CI2SL, where you can find more information about that webinar and also register if you are interested. With that, thank you very much. Thank you, the speakers. Thank you all for attending the webinar.
Thanks.
Thank you, Bill. Thank you for all of you who were helping to answer the questions in the Google Doc. I'm going to close the webinar. It won't kick you out. But remember, feel free, if we didn't get your question answered, to put it in the Google Doc so that we can make sure we get you an answer. And I just want to echo what Osni said. We are looking at working with Bill and team to develop some additional training. It's really important that you could let us know in that survey really what specifically you would like to learn more about. That will really help us as we move forward in the next month, developing additional training. Thank you all for your time. Have a great day, and we'll hopefully see you next month. Thank you, Bill. Thank you, Osni.
Thanks.
Sure, thank you.